Can you think of a time when you've had a hardware or link failure in your network? If you didn't have high availability, the result may have been catastrophic. This carries extra importance for firewalls, as that's often where connections to the internet and WAN links live. We're now going to see how high availability works on Palo Alto firewalls and how it's configured. When it comes to high availability, Palo Alto firewalls use the same two options as everyone else. Option 1 is active-passive, where one firewall is in a passive state waiting to take over if there's a failure. Option 2 is active-active, where both firewalls actively pass traffic. Active-passive is the simplest type of HA to deploy. In this model, one firewall is analyzing and passing the traffic, learning routes from routing protocols, maintaining information about sessions, and so on. The second firewall is turned on and physically connected to the network, but it does not do much. That's why it's called a passive firewall. It's just waiting until it's needed. It will synchronize information from the active firewall, such as firewall configuration, session information, and things like this. If the active firewall fails, the passive firewall is there to take over. The alternative option, active-active, has both firewalls processing traffic at the same time. That is, they share the load. If one of these firewalls fails, then the other one takes on the extra traffic. Keep in mind that a single firewall needs to be powerful enough to take on all the traffic if a failure like this happens. Active-active is a bit more complicated to set up, as you need to think about how traffic is distributed between the pair and how NAT pools are managed on each device. We'll talk a little more about this and other active-active considerations at the end of the video. In both HA models, each firewall has a priority. In active-passive, this priority decides which firewall is active. In active-active, the priority decides which firewall is the active primary firewall. Priority comes into play if preemption is enabled, which we'll see a little bit later. This is also important when a failed firewall has been repaired and added back into the pair. When configuring an HA pair, it is mandatory to configure a few special links between the two firewalls. Most Palo Alto firewalls come with dedicated ports for this. In this model, we have the dedicated HA1 and HA2 ports. HA1 is called the control link. This exchanges control plane type traffic between the two firewalls. This includes heartbeat messages, HA state information, routing table synchronization, and user ID. HA2 is the data link, as it's used for sharing data plane type traffic. This includes synchronizing sessions, forwarding tables, IPsec tunnel information, and ARP information. Not all models have the exact same ports though. The model shown here has HA1A and HA1B, which are the primary and backup control links. Instead of a port named HA2, it has an HSCI port. This is a high-speed data link. Some of the bigger firewalls have an additional AUX port. On the other end of the scale, we have smaller firewalls which do not have any ports dedicated to HA. We still have options though. In a case like this, we would configure some of the regular ports for HA. These are in-band ports. We can even use the management port for the control link if we want to. Even on the bigger models, we can still use in-band ports. Think of this one again, which only has one HSCI port for the data link. In this case, we can configure an in-band port as a backup data link. In fact, this is highly recommended, and we'll see how this is configured in a few moments' time. When we're talking active-active, we also need to configure an additional link called HA3. This is a packet forwarding link. This is used when setting up sessions and passing transit traffic from one firewall to another. This link is entirely layer 2 and uses MAC-in-MAC encapsulation. You'll probably have noticed that there are no dedicated ports for this, so we would need to configure an in-band port. The HA links can be run through external switches if you want them to. The control links can be routed, with traffic passing through multiple subnets. But where you can, it's recommended to connect the firewalls directly together. I'll include a link to some best practices in the description if you want some extra reading. So obviously the point of HA is to protect against failures. Roughly speaking, we can group failures into 3 categories. The first is a firewall failure, where one of the firewalls stops working for some reason. The second is uplink failure, where a link connected to the firewall goes down. The third is path failure, where something upstream of the firewall fails. Of course, there is a scenario which we're not talking about here, which is when an administrator manually causes a failover, perhaps to install an update. We'll look at that in the next video. During regular operations, the firewall pairs send each other regular heartbeat messages across the control link. This is just a simple ICMP ping. By default, these are sent out once per second, and if 3 in a row do not arrive, then the partner is assumed to be lost. We can change the heartbeat timer using timer profiles, which we'll see briefly in a moment. The recommended profile is the default, but there is also aggressive, or we can create our own. Some high-end firewalls perform internal health checks. This is not something we can configure, it just happens on its own. If a health check fails, this will also mean the firewall has failed and trigger a failover. An uplink failure occurs when a link directly connected to the firewall fails. The firewall itself is fine though. And we're not talking about our HA links here. We're thinking about links to switches or routers. Even though the firewall is still alive, it won't be able to forward traffic. So we configure the firewalls to watch the state of individual links or groups of links, and if enough of them fail, this can trigger a failover. The third consideration is path monitoring. This is where something that is not directly connected to the firewall fails. This might not sound so bad, but if it's a critical upstream router, it can still break our network. Depending on the way the network was designed, we may want this to cause a failover so as to take an alternate path. We can do this by configuring path monitoring, which uses something like ping to see if a device on the network is up, and if it's not, the firewall can take action. Let's see how this is configured. To give you a bit of background, I'm configuring 2 Palo Alto 3260s. So far, I've set a management IP on each, but other than that, I have made no changes to the config. The HA1A and HA1B ports are directly connected with Cat6 cables. The HSCI interface is also directly connected with a 10 gig twin-X DAC cable. There's no dedicated backup for the data link, so I've also cabled up the Ethernet 1/20 ports. We are now going to configure active-passive HA. Firstly, we'll check if ping is enabled on the management interface. This is not the most important thing for us in this specific case, but if you have a smaller model, you might be using these interfaces as your control link. And you'll remember that ping is used for heartbeats, so we need to make sure this is allowed. In any case, for us, it's enabled out of the box. Next, we're going to select our HA ports. This model already has 3 of our needed ports, so we don't need to do anything special for them. We do want Ethernet 1/20 to be a backup data link though, so we need to configure that. Keep in mind that a backup link is optional. Under the Network tab, we go to Interfaces. If you look closely, the interface icon for Ethernet 120 is slightly different to the rest. When we open the interface, we change the type to HA and optionally add a comment. Time for the real HA config. This is in the Device tab under High Availability. In the Setup area, we add a group ID. This needs to match on both our firewalls. This is also where we select whether we want active-passive or active-active. We'll obviously leave ours as active-passive. We'll come back to the rest of these options later. Next up is the control link. That's the HA1 interfaces, which are configured in the sections over on the right. In port, we select the physical interface that we want to use as the primary control link. For us, that's HA1A. This operates at layer 3, so we also need IP addressing. I'm using 169.254.1.1, as this is a subnet that should never be routable anywhere on my network. That makes it a good choice for this out-of-band subnet. Notice that we include a default gateway. We would use this if we have our firewalls in different subnets. As I just mentioned, our two firewalls are in a non-routable subnet, so we can leave this blank for this example. Another option is encryption. I'm not going to worry about that in my case, as these firewalls are directly connected and they are in a secure server room, so there's really no risk of anyone seeing this traffic. It's the same procedure for the backup control link, just use the HA1B interface. Also, assign a different subnet to the backup link. The primary and backup cannot overlap. Now for the data link, which is using the HSCI port. Notice that there are options for transport. We're going to use Ethernet as our firewalls are directly connected. However, if we connected them through external switches, we would need to change this to TCP or UDP and set an IP address. We also want to make sure session synchronization is enabled. If it isn't, and there's a failover, the new active router will need to build all those sessions again, which would be disruptive to the flow of traffic. And finally, let's enable keep alives over HA2. This sends additional keep alive messages between the two firewalls. This is in addition to the heartbeats we talked about earlier. If the keep alives go missing, then the firewalls know there's a problem. This would be particularly useful if we're running these links through external switches and there's an upstream failure that the firewall wouldn't normally detect. And of course, we're configuring the backup HA2 link using the Ethernet 120 interface that we prepared earlier. In election settings, we should enable heartbeat backup. We do this because we're using dedicated HA interfaces. If we were using the management port as our control link, we wouldn't need to do this. So what is it? Heartbeat backup prevents a split brain scenario. Imagine if HA1 went down for any reason. In this case, heartbeats would go missing and both firewalls would think that the other has failed. They would then both try to become active. The backup heartbeats use another path, so the firewalls are able to see if the other firewall is really down. We can also set the device priority here if we want to. This is optional, but it helps us to know which firewall is active under normal circumstances. The lower the value, the more preferred that firewall is. If both values are the same, as they are by default, then the lowest MAC on HA1 is used to break the tie. I like to enable preemption. This means that if we replace a failed firewall and the replacement has a better priority, it will automatically become active. Here is where you can change the timers that I spoke about earlier. I would suggest leaving them as recommended unless you really have a need to change them. By default, a passive device will keep its interfaces in a disabled state until it transitions to active. Changing this to auto means that the interfaces on the passive unit will always stay up. This is a step toward faster failover, but it might make troubleshooting more difficult. Even if we do this, the passive unit will not forward any traffic through these interfaces. So, make sure that any switches or firewalls connected to these interfaces are not trying to forward traffic through here based on link status. If you find that you are inexplicably dropping traffic, maybe come back here and check this setting. If you do set this to auto, you can also enable LACP and LLDP pre-negotiation. This is the next step to fast failover. If you're just not sure, leave it as shutdown. Well, that's our prerequisites done, so we can finally enable HA. This is in the same section that we saw earlier. Make sure Enable Config Sync is turned on. If it's not, the config will not be replicated from the active to passive. We need to enter the IPs of the peer device here. And finally, we're committing our changes. The second unit needs to be configured too, but as it's more or less the exact same as this one, I'll save your time and pause the video while I do that. The second unit is now done. If we go to the dashboard, we will be able to find a widget for high availability. In this widget, we can force a sync of HA information to the peer device. Notice that the status of the device is active and the config has been synchronized. If you're interested in active-active, stick around. we've got a few brief concepts to cover. In the active-active model, both firewalls need to forward traffic at the same time. This comes with some extra considerations. When a session is created, which firewall owns it? How is traffic split across the two firewalls? Is it evenly shared, or does one take a larger load? How do you direct traffic to the right firewall, and what happens if traffic arrives at the wrong firewall? When new traffic reaches the firewall sets up a session. This is where the firewall starts collecting information about the flow of traffic so it can track it. This is not specific to HA at this point. Even a standalone firewall will do this. When you have two active-active firewalls, one firewall will become the session owner. Under normal circumstances, this firewall will handle all traffic for the session. If it fails, the other firewall can take over as the session owner. In general, the firewall that receives the first packet in a flow will become the session owner for that flow. However, there are times when we might want to change that. For example, we might want the active primary firewall to handle all traffic for the purposes of packet capturing or some other troubleshooting. We might also decide to use another method to determine which firewall becomes the owner. The two other options are IP hash, which uses a hash of the source and destination IPs to allocate sessions to the firewalls, or IP modulo, which uses the parity of the source IP. The firewall that receives the first packet is often the best choice. But if we do that, how can we split the traffic somewhat evenly across the firewalls? That is, how do we prevent all traffic arriving at a single firewall and that firewall becoming the owner of all traffic? There are a few ways this can be done. One option is to use layer 3 routing, where the upstream routers decide which firewall a packet should be delivered to. Or maybe a layer 2 floating IP address with ARP load sharing would be better. This is a bit like VRRP. A third option might be to use an external hardware load balancer. The option you choose has to be the right one for your network. But let's consider this scenario. A packet arrives at one firewall, and this firewall sets up a session and becomes the session owner. For some reason, the next packet in the flow arrives on the other firewall. What happens now? In this case, the packet needs to be passed on to the correct firewall. That's what the HA3 link is used for. That's also why the HA3 link is only needed for active-active HA. Once the packet is passed to the correct firewall, it is processed as normal. We've seen the two types of high availability on Palo Alto firewalls. Hang around for the next video where we will see how to update these firewalls that have been configured as an HA pair.